Yes. Today we will discuss about field effect transistor. Till now we studied about the bipolar junction transistor. In that, current is produced due to the majority and minority charge carriers. So it is called bipolar junction transistor, and it is a three-terminal device. So the three terminals are emitter, base, collector, and the main application of BJT is amplifier. And other applications of BJT are switch, and it can be used in the digital circuits and oscillator circuits. Yes. So today we will discuss about the field effect transistor. This is unipolar transistor. BJT is bipolar. Field effect transistor is unipolar. Why it is unipolar? Here current is produced due to the only majority charge carriers. So it is unipolar junction transistor. So this unipolar transistor is also used as a amplifier and switch. Then we already know BJT is used as a amplifier and switch. Then why we need to study about the field effect transistor? What are the drawbacks in the BJT? Yes, field effect transistor, we know there are two types. There are junction field effect transistor and MOSFET, metal oxide semiconductor field effect transistor. These two are unipolar device. So current is due to only majority charge carriers. Yes, these field effect transistors, either JFET or MOSFET, are called voltage control device because voltage applied at gate terminal will control the current flow in the channel. Yes. So similar to BJT, it is also three terminal device. Is field effect transistor also. Here we are having the source, drain, and gate. These are the three terminals. So these JFET and MOSFET or field effect transistors are called voltage control device because here applied voltage at gate will control the current in the device. Yes, BJT is called current control device. Why? Because we know the current, collector current or output current IC is controlled by the base current, input current IB. Yes, so output current IC is controlled by the base current IB. Then the BJT is called current control device. Here in the field of transistor, the applied gate voltage is or gate to source voltage controls the drain current. So that's why this field effect transistor is called voltage control device. Clear? Why it is named as field effect transistor? Because here the output current flow is controlled by the electric field set up in the device by an external applied voltage between the gate and source. Yes. So that's why we are calling this is field effect transistor. The output current flow is controlled by the electric field set up in the device by an externally applied gate voltage. That's why it is named as field effect transistor. What are the drawbacks in BJT and what are the features of FET? So we know in BJT thermal runaway is present. Thermal runaway is nothing but by increasing the temperature, reverse saturation current increases in the BJT. Due to that, power dissipation produced at the collector junction. Due to that, heat produced at the collector junction. So this cycle again heat produces means again temperature increases. When this cycle repeats again and again, then collector junction will break down. So this is called thermal runaway or your transferable damage. So thermal runaway is present in the BJT, but in the field effect transistor it does not occur. Yes. So in field effect transistor we don't have any thermal runaway. So there is no damage of field transistor. Yes. So we can say this field effect transistor can operate at higher temperature, or we can say this field effect transistor is more stable at higher temperature compared to the BJT. Yes. And one more reason, this field effect transistor has very high input impedance compared to the BJT. Yes. So we know the main application of BJT is amplifier, and I said this field effect transistor is also used as a amplifier. Then, so when we are designing the amplifier circuit, we require the high input impedance. So compared to the BJT, we are having the field effect transistor having very high input impedance. Generally, it is in the mega ohms. So it is one of the advantage to use this FET as amplifier. Yes. So, and third one, the size of the field effect transistor is very small compared to the BJT. Yes. So, as an engineer, while we are integrating the all these, while we are making the integrating circuits, that means the number of transistors are keeping on single silicon wafer. Then it is called integrated circuits. So nowadays we are using the all our integrated circuits. In that we are keeping the millions of transistors on single silicon wafer. Yes, when size of the single FET is very small, then we can accommodate more number of transistors, more number of field effect transistors compared to the BJTs. So this is also one of the advantage. So we can say the features of field effect transistor is, first one, thermal runaway does not occur in the field effect transistor. So we can say it is more stable at a higher temperature compared to the BJT. And second one, this field effect transistor offers the very high input impedance compared to the BJT. So while we are designing the amplifier circuit, we are always choosing the high input impedance. Yes, and third one, the the size of the field effect transistor is very small compared to the BJT. So due to this reason, we can accommodate the more number of transistors in a single silicon wafer or in integrated circuits. So these are the three basic reasons to use this field effect transistor over the BJT. Now we'll discuss about this field effect transistor construction. So we know these field effect transistors are two types, that are JFET and MOSFET. Again, JFET is classified as N-channel JFET and MOSFET P-channel JFET. Again, similarly, MOSFET is depletion type, enhancement type. In the depletion, N-channel depletion, P-channel depletion. Enhancement, N-channel enhancement, P-channel enhancement. So this classification of transistors is already discussed in the starting of PJT. You can check in that. Yes. So today we'll discuss about the N-channel JFET. Okay. So here JFET is also a three-terminal device. The three terminals are named as source, drain, and gate. These three are similar to the BJT terminals: emitter, gate, emitter, base, and collector. Yes. So here we'll see construction of N-channel JFET. So moderately doped N-type semiconductor is used as channel. So now I am saying the channel is N-type material. So moderately doped N-type semiconductor is used as a channel in the JFET. One end of channel is called drain, other end of channel is called source. So when I consider the N-type material as channel, so one end is called source, other end is called drain. Yes, and here carriers flow through the channel. So that means the carriers flow through the N-type material from source to drain. That means one end to another end. Then we can say the current is due to the majority charge carriers. Here the current is due to the electrons. Yes. So here we can say one end is called source, another end is called drain. So here current or electrons are moving from the source to drain in the channel. Yes. So now electrons are moving from the source to drain. Then we can say the current direction is from drain to source. Yes. So here two heavily doped P regions are created on either sides of the channel. So here you can observe the diagram. So here source and drain is mentioned here. In that two heavily P regions are created on either sides of the channel. These P plus regions are internally connected to each other. They act as gate. So you can observe here P plus regions. The two are mentioned. The two are internally connected to each other. Yes, the terminal is called gate terminal. So now we are having the three terminals: source, drain, another one is gate. The source and drain are moderately doped one. So the channel one end is called source, another one is called drain. Yes, the middle part is called channel, and two heavily P regions are created on either side of the channel. So when we are considering the channel is N type, then gate material must be heavily doped P type. Yes, if I am considering the P type material as channel, then N heavily doped N regions are called gate terminals. Yes, so now we consider the N channel, that P plus regions are acting as gate terminal. So junction between the P plus gate and N type channel is called channel junction or gate channel junction. So now you can observe P and N type materials. Yes, it is always kept in the reverse bias, which helps in controlling the channel length. So this gate channel junction is always connected in the reverse bias, which helps in the controlling the channel width. So why? Because when you are increasing the, that means the gate is made up of P type material. When we are applying the reverse bias means negative terminal of the battery. When you are applying the more negative potential at the gate terminals, what happens? So that gate is the gate is in reverse bias. Then the depletion region will form at the gate channel junction. So we are increasing the more reverse bias. What happens? The depletion width increases. Yes. How it is increases? So we can say gate is heavily doped one, channel is lightly doped one, N type material. So in the P junction we already know. So the depletion width is always penetrating towards to the lightly doped region. So here lightly doped region is N channel. So when you are increasing the reverse bias voltage to the gate to channel, then what happens? Then the more depletion region penetrates towards the channel, then what happens? The width of the channel will be decreases. So we can say this gate to channel junction must be in reverse bias because it controls the channel width. Yes, the source, drain, gate. So source is nothing but it is the end of the channel through which majority carriers enter the channel. So source is nothing but it is one end of the channel which allows the or which allows the majority charges carriers enter into the channel, and drain it is another end of the channel, so which majority carriers leave or exit the channel. Clear? Next, gate, it is a heavily doped regions which helps in controlling the channel width. In previous only we discussed. For the proper operation, we said the JFET has two voltages. One is VDS, another one is VGS. So this VDS is nothing but the potential between the drain to source, and VGS is nothing but potential between the gate to source. So to get the proper operation of JFET, we must apply the two potentials, that are VDS and VGS. So VDS is nothing but it is applied so that majority carriers drift through the channel from source to drain, which results in a current known as drain current. So VDS is applied between the drain to source. Yes. So when you are applying the potential between the drain to source, what happens? Majority charge carriers drift from the source to drain. Drift from the source to drain. Then charge carriers are moving in the channel from source to drain. The resulting current is called drain current or drain to source current. Yes. So now we assumed the n channel JFET. So now we assume the n channel JFET. So to drift the electrons from source to drain, we must apply the positive potential at VDS. Why? Because when we are applying the drain is positive, then what happens? The positive terminal of the battery is connected to the drain and negative terminal of the battery is connected to the source. So here the source is in forward bias, so we can say it is connected to the negative terminal of the battery. So the battery is always repels the electrons from the source. These electrons are moving from the source through the channel, then these electrons will reach the drain. Why? Because the drain is connected to the positive terminal of the battery, so the drain attracts the electrons from the source. So this VDS is used to drift the majority charge carriers from the source to drain through the channel. Yes. So for the n channel JFET, we must apply the VDS is always positive. Yes, electrons is always flow from the lower to higher potential. Yes. So for the positive, for the n channel JFET, VDS must be positive. For the p channel JFET, we can say VDS must be negative. Yes. So then only hole will drift from the source to drain in the p channel JFET. Yes. This VGS is applied between the gate and source terminals. It is always, we said, reverse bias. Why? Because to control the channel width. Yes. So when you are increasing the more VGS, that means gate is positive. So we are applying the positive potential to the gate. So then it is in the reverse bias. So the width or depletion width increases at the gate to channel. So it controls the width of the channel. Yes. So VGS is always negative for the n channel and VGS is always positive for the p channel. Yes, you can observe here. So here we'll discuss about the operation of JFET. In this we applied the VGS and VDS. So first case you can observe in the first diagram, no bias voltage on gate. Just simply we are short circuiting the gate and source, gate terminals 2 short circuited and which are connected to the ground, and we applied the VDS is positive. Why? Because to get the small amount of current. In second case, we are considering the small negative gate potential. Why? Because to make in reverse bias, and we are applying the VDS, more VDS. Yes. And third case, we are applying the large negative gate, and again we are applying the VDS. So here we are considering the VDS is constant and VGS is varying from initially 0, then after small VGS, then after large VGS. Yes. So while we are discussing about the JFET, here VDS is applied because to drift the charge carriers from the source to drain. So now we discuss about the n channel JFET. So VDS must be positive to drift the electrons from source to drain. Yes. So now this is constant, VDS value is constant. Yes. And we are controlling the channel width by changing the gate to source potential. That means initially we are applying the VGS equals to 0, then VS is very small, then VS is very large value, negative large value. Yes. So in this operation, first case we let VDS to be constant and vary the VGS from 0 to negative values. Yes. If VGS is 0, then what happens? Then reverse biasing of gate channel junction does not occur. So now when you are keeping the VSC 0, there is no gate channel, there is no reverse bias of gate channel junction. Yes, hence full channel width will be available for the conduction. So there is no depletion width. So we can get the maximum width to get the conduction. Yes, in this case, we consider the VDS is constant. That means this VDS is used to drift the electrons from source to drain. So when depletion width, when channel width is more, and we are applying the VDS is constant, so the maximum number of electrons move from source to drain. Yes, this is the maximum current. Yes, this is the maximum drain to source current or maximum drain current. This current is called drain to source saturation current. It is mentioned as IDSS. Yes. So when we are not applying the VGS, that means when we are applying VGS equals to 0, then there is no depletion region formed between the collector and there is a depletion region formed between the channel and our gate. Yes, so we can get the maximum channel width, we can get the maximum channel width. So in that, when we are applying the constant VDS, we can get the maximum current. This maximum current is called drain to source saturated current. This is called IDSS. Yes, now in this I am considering VDS is very small. Again, VDS is constant. Yes, when you are applying the VDS is very small in negative, that means now gate to channel junction becomes reverse bias. Yes, now gate to channel junction is in reverse bias. We know depletion region will increase in that. Why? Because gate is P plus region and channel is material. So depletion region will form. This depletion region is lightly, this depletion region is more penetrates into the lightly doped material. Yes. So here lightly doped material is channel compared to the gate. So depletion region will penetrate more into the channel. Due to this, what happens? The net channel width will decrease. Yes. So the net channel width is decreases. Thereby electron flow from source to drain also decreases. Source to drain also decreases. So thereby what happens? Current from drain to source also decreases. So when you are applying the small VGS negative potential to the N channel JFET, that gate channel junction is in reverse bias. Depletion region forms and it is more penetrates into the channel because it is lightly doped compared to the gate. Due to this, net channel width decreases, thereby electron flow from source to drain will be decreases, then current also decreases. Yes, so here you can observe diagram. So when I am applying the very small and VDS is constant, so very small depletion width is formed. Yes, and next this is made strongly. Now we applied the more negative at gate. Then what happens? Depletion region forms more and it is more penetrates into the channel. That means it is fully occupy the channel. The net depletion width becomes 0. When you are applying the more negative gate to source potential, what happens? It is more reverse bias, then more depletion region penetrates into the channel, then net channel width becomes 0. Therefore, electrons cannot flow from the source to drain. So in this what happens? So there is no electrons moving from source to drain, then we can say the drain current is 0. Yes, clear? So when depletion region fully occupy the channel, channel is said to be pinch off. Yes, when depletion region fully occupy the channel, then channel is said to be pinch off. This corresponding VGS value is called pinch off voltage. So yet particular VGS value when depletion region fully occupy the channel, that voltage is called, that gate to source voltage is called pinch off voltage. Yes. So now we can observe the transfer characteristics of the JFET. So this transfer characteristics is always drawn between the input parameter and output parameter. Yes, input to output parameter. Yes, so here VGS is input voltage and IDS is output current. So transfer characteristics is always done between the input and output parameters. Any input parameter, any output parameter. Yes. Now it is drawn between the VGS and IDS. So when VGS increases more negative in the N channel JFET, at particular point this IDS is 0. Yes. That potential is called, that VGS is called, what is called? It is called pinch of voltage. So from this we can observe, from this graph we can observe this N channel JFET has pinch of voltage negative. Yes. So while we are considering this graph between the VGS and IDS, we assume the VDS is constant. Yes. So these transfer characteristics are mathematically represented by the following equation. It is equals to IDS equals to IDSS into 1 minus VGS by VP. So IDS is the drain to source current. IDS is the drain to source saturated current. It is nothing but maximum possible IDS value. Yes. So in diodes we are using reverse saturation current is I naught. So it is occur in the reverse bias. Here IDSS is nothing but IDSS is nothing but drain to source saturated current. It is the maximum possible IDS value. Yes. So this equation is also called as Shockley equation, and it is IDS equals to IDSS into 1 minus VGS by VP. So VP is nothing but pinch of voltage. Yes. So similarly for the P channel JFET, the pinch of voltage must be positive. Why? Because to make the gate to channel junction in reverse bias, we need to apply the VGS is positive. So the pinch of voltage is positive. Yes. So this pinch of voltage is also called as VGS off. VGS off. Clear? What the how to calculate the pinch of voltage. So now we'll discuss how to calculate the pinch of voltage here. It is represented with the VP. So we said that gate to channel junction is in a reverse bias and gate is more doped one, channel is lightly doped one. So it is P plus N junction. So we know the depletion width for this P plus N junction. So it is already discussed in the PN junction diodes. So we can write depletion width equals W equals to under root of 2 epsilon VB by E into ND. Yes, ND is nothing but donor concentration. Why? Because the depletion width is more penetrates into the lightly doped region. It's nothing but N region. So N region is concentration is ND, donor concentration. Yes. So it is all discussed in the pre-nation diodes. So that VB is nothing but barrier potential, net barrier potential. It is equals to V naught built-in potential plus applied reverse bias voltage. So built-in potential VB equals to V naught is barrier potential VB equals to V naught. It is nothing but built-in potential plus VGS. It is nothing but reverse bias voltage. So here I kept the magnitude only. Yes. For N channel it is negative value. For P channel it is positive value. So when Vs equals to Vp, that means some particular point the depletion region, the net depletion width becomes 0. Yes. So here I am considering the depletion width W equals to A. So we can write Vs equals to Vp, then I consider W equals to A. So I substitute here. So A equals to under root of 2 epsilon E Vb by E into Nd. So here I said Vb equals to V naught plus Vp. Why? Because V naught plus Vgs, but I replace Vs with Vp. So now we can write 2 epsilon Vb by E and D equals to A square by squaring on both sides. So from that we can write Vb equals to A square E into Nd by 2 epsilon. So I defined V naught equals to VB equals to V naught plus VP, but the built-in potential is very small compared to the pinch off potential. So I can replace it is equals to A square E N D by 2 epsilon. Yes, from that we can write VB equals to VB equals to, yeah, it is, I mentioned VB, but it is VP. Yes, VP equals to A square E N D by 2 epsilon. Yes, so from this we can say this pinch off voltage VP is directly proportional to the concentration of channel doping concentration of channel value. Yes, so for n channel JFET VP is negative, therefore minus sign should be added to the above equation. Yes, and VP is depends on the channel width. So why? Because it is directly proportional to the A square and doping concentration. Yes, and it is always independent of the channel length. Clear? So this pinch off voltage is directly proportional to the channel width and doping concentration, and it is independent of channel length. Here we are not discussing about the length of the channel. Clear? Case 2. In first case we discussed when VDS is constant and VGS is varying from the 0 to more negative values. Here now I am considering the VGS is constant and I am varying the VDS from 0 to positive values. Why? Because we need to apply the drain as positive potential. Why? Because to drift the electrons from source to drain for the n-channel JFET. So let VGS be constant at 0 volt. Yes. So VGS is constant at 0 volts. If VGS is small, then electrons cannot drift from the source to drain. Why? Because when we are not applying the potential at the drain, so it cannot drift from the source to drain. So we can say the drain to source current or ID current is 0. Yes. Now I am applying the VDS is positive and very small values. Then what happens? A finite drain current starts flowing. Yes, why? Because I am applying the positive at the drain and negative at the source. Then what happens? The electrons moving from the source to drain that are very small current. Yes. So from this we can say IDS equals to VDS by RDS. Here RDS is the channel resistance. Yes. So it's nothing but enter material. So this enter material is also offering the resistance. So here enter material is acting as a channel. So we can say IDS equals to VDS by RDS. So RDS is the channel resistance. Now I am increasing VDS. Then what happens? So if I am increasing the VDS, the drain current increases linearly. Why? Because so more electrons will drift from the source to drain. Then what happens? Channel resistance will be decreases. Yes. Next, I am increasing more. Now VDS is positive and very large. Then positive voltage will appear across the length of the channel. This voltage is maximum. That means this VDS is more present. The positive voltage more present at the drain and it is gradually decreased towards to the source. So more positive or more maximum value at the drain and it is gradually decreasing towards the source along the channel. Yes. So channel voltage decreases because of voltage drop. So channel voltage gradually decreases because of voltage drop. So the positive channel voltage will cause the reverse biasing of gate channel junction. So now here the channel having the positive potential closer to the drain, then what happens? That gate to channel. Why? Because here channel becomes positive and gate is negative, but it is constant. It is zero potential. Yes. So now channel to gate junction becomes reverse bias. Hence again it forms the depletion region. So depletion region appear at the channel. Yes. So depletion region has greater width at drain end. So more potential present at the drain and less potential at the source along the channel. As you can observe this potential, so here at some point 1 volts, then it's moving towards the drain. Now it is 2 volts, and then after 3 volts, and then after 4 volts, and maximum VDS is present at the drain and minimum present at the source. Yes, due to this reason, channel junction becomes the reverse bias. So we know depletion region forms. So this depletion, when depletion region forms, then what happens? More depletion region penetrates into the channel. That too towards the drain. Why? Because at drain side we are having the more positive potential. Yes. So this depletion width is also decreases along the channel length. Yes, due to appearance of this depletion region, channel width reduces and channel resistance increases. So when depletion region increases, then what happens? Automatically resistance also increases. Therefore, current IDS increases slowly. Yes, if VDS is VP, then what happens in this case? So channel gets again pitched off at drain end because gate to channel voltage at drain end becomes VP, that is pinch off voltage. So you can observe here. Yes. So if we are increasing more VDS value and it is greater than the pinch off voltage, then channel pinch off occurs at some distance of delta L away from the drain. So the excess voltage is VDS minus VP will appear across the delta L distance. This delta L is nothing but so distance from the drain to the channel. Yes, at that point completely net channel width is 0. Yes, so here delta L is very small and high electric field. It offers the high electric field in this. Why? Because it is in depletion. It is depletion region. So the depletion region having the immobile charge gas. This immobile charge gas will produce the higher electric field. It is equals to V by R, voltage by distance. So here net voltage equals to VDS minus VP. Delta L is nothing but distance in the channel from the drain to pinch off voltage, pinch off point. So when delta L is very small, then what happens? Electric field intensity is also very high. Yes, so high electric field is produced or develops in the very small delta L distance. So this what happens then when electrons coming from the source and enter this high electric field. So now electrons are coming from this source and these are passing through the channel at some point or at delta L distance point from the drain. So it is pinched off. So that means electrons are entered into the high electric field region, then their velocity gets saturated. So it is already discussed in the semiconductor materials only. Yes, at higher electric field, so velocity of the charge gas is saturated, that means constant. Thereby what happens? Then drain current becomes constant. Clear? So now that current is constant in this period when we are applying the VDS is greater than VP. Clear? Thank you.